get no data.
All right, careful, you're on camera.
That kind of makes me feel better about my board not working. I like just really disheartened when my board just stopped working.
What board?
My
On the satellite?
Yeah, on the satellite, but for this solid state detector, I had an analog board and a digital board. And everything was working like really well, exactly what I was expecting it to do. It was integrating with the processor guides, like perfectly. It wasn't taking much time to integrate with them, maybe all the time.
Hey, dude.
And then I move on to the next step.
Sure.
And at 7 a.m. and out of the
I was
board,
like
we were
totally
supposed to integrate with daily.
spaced out.
It
and
just,
forgot.
the digital board just stopped.
This is
It's not
yeah, it's not
doing-
trying to be very
Like,
good.
it's
I
not
literally
doing
just
anything with the
forgot.
signals coming in, it's not, like, it's not doing
He
anything.
said that,
I'm not
like,
even getting the
he's like, yeah, he's
roles,
like,
I'm getting
I saw my
roaming,
mom
so
like
that's
a
it.
minute ago.
And I've been
to
through
go
it, I
talk
like
to
replaced parts, and I can't get it to do anything.
Trying to skip.
You okay? Sorry.
Yeah, welcome to research.
It's just like, the worst part is like, if it had been struggling to work the entire time,
Mm-hmm.
then it wouldn't have been so disheartening. But it was working really well, and then like, it was taking less time to program mine than it had with all the other instruments, so it was like, it was doing, it like, wasn't just being like good, it was being really good. And then,
I turned mine off.
at the
Oh, on average then.
I totally just didn't think about
But I expected Dr. Boss to chew me out, and all he said was, you gave it the good college try, and I was like, okay,
Had anybody seen it working well?
yeah, Piercy and Colin, like, they'd all seen it, and I'd been doing the same.
So at least you don't feel like you're going crazy. All right, so is Clayton not coming?
Clayton's not coming.
I think Blake is.
Blake is not coming. Blake's
not?
gone.
Blake's gone?
Blake's gone.
What?
The football had to leave at 3 something, so.
Is there that?
That's what he told me, so.
I heard he's.
All right.
Huh?
Yeah, you better hope that I don't see a football player around here at 4 o'clock. Because, you know, then it's in the pickle.
Speaking of skipping class, guess what happened to me today?
What?
So
You slept through your class?
No, so, well,
Although that would be
that's
surprising.
not exactly exciting, but, so, I get out of controls today, and I'm like, I want to go get my modern lab done before lunch. But I forgot that I had modern physics right after controls, so I just like went into the computer lab and finished up my modern lab. I got done at like 12:30 and then went to lunch. Then I get out of lunch and I see Blake and he's like, dude, where were you in modern? I was like,
I was doing modern.
I was
Oh shit, I forgot to turn my.
yeah, we should have story time.
What chapter are we
You
in?
can impart on us some wisdom from the engineering field.
We do that one? Oh no, we already did that
Help
one.
me do my clash plans.
We're on to chapter 9.
Dude, I'm about to go lumberjacking tonight.
Okay, so
Need to have it.
we have discussed 6 unique stresses on any that exist at any point in material. Sigma in the x direction, sigma in the y direction, and sigma in the z direction, the normal stresses. Tau yz, tau xz, and tau xy, the shear stresses on the 3 phases, 3 dimensions. So that's really kind of complex to have to keep track of all 6 stresses in a material. Fortunately, there are a lot of geometrical constraints that will actually simplify that down so we don't have 6 stresses to deal with. For instance, and a surface. So let's take a little element of mass on the surface. And here we could have a tensile force in the, what did I call that? That was the x, I think. X direction, we could have sigma y, a normal stress in the y direction. There's no sigma z, because there's nothing to apply or pull, to push or pull on the surface, because it's a surface. Right, so there's no material here to push or pull. Similarly then, we would have a tau on the y plane acting in the x direction, and a tau on the x plane acting in the y direction, and those two would be equal because there's no net moment on the component. And there's similarly then shear stresses on the back faces that complementary shear stresses. But again, we can't have shear stresses on the top either because there's nothing to resist a stress, right? So you can't have a stress applied to the top unless I actually have something up there to push on it and apply that stress. So really, in this case, we boil at a surface, we boil down to 2 normal stresses and 1 shear stress, but all of those exist in kind of a planar configuration. So if you look up there on the board in the upper left-hand corner, that is this viewed from above. We have a tensile stress pulling in the x direction, a tensile stress pulling in the y direction, and then a shear stress on the x plane pointing in the y direction, and a shear stress on the y plane pointing in the x direction that must be equal by conservation of, by sum of the moments equals 0. Okay? We call this configuration plane stress. Because it's stress that exists in the plane. These guys are getting a little loud, so. Okay, so we call this a condition of plane stress. So oftentimes, even in a thin member, even if we're not at the surface, if we have a thin plate, we can still consider that the stress condition in that thin plate is plane stress. Okay? Potentially. Or if it's a thick plate and we look at the surface, there's different conditions in which we can have this state of plane stress in real life. Now, in this particular configuration, so let me draw it on the board.
What is the character that's for shear stress? Is it tau?
Yeah. Right, so there's the picture. But what happens if the geometry of our component happens to not line up with this x and y? In other words, what happens, I have this next. Yes. What happens if we're aligned at some odd angle, theta? So that we have this x prime, y prime coordinate system, which is oriented at some angle theta relative to our xy prime, our xy coordinate system. So this could happen either because the component is twisted in a field where the forces or stresses are being applied in that direction, or the stresses, we calculate the stresses most conveniently in the x prime, y prime configuration, but our components in the xy, whichever way you look at it. And so in other words, I'm not always going to load a plate perpendicular to its directions. Right? So I may have these odd angles. So we've got to be able to transform this into this. Okay? And you notice that if you do the sum of the forces here, the sigma sub x prime, the normal stress in the x prime direction is not equal to the normal stress in the x direction. You see what I'm saying? This is not equal to that. That is not equal to that. Because a component of sigma y will act in the sigma x prime direction. And a component of sigma y will act in the sigma y prime direction. So the sigma y will be split into x prime and y prime components. Sigma x will be split into x prime and, in this case, minus y prime components. Right? So the components, and the same thing is true for the shear stresses. So the components all get split into different directions, and it's a little bit of a mess. So how do we do it? So what we're going to do is we're going to find the sum of the forces in the x prime coordinate system based on what we started with. So in other words, we're going to draw a little line here. We're going to take a little wedge out of the corner of this system and zoom in on that wedge. We're going to take this little chunk here and take that corner out, right? Because that's actually, I didn't draw that very well. Okay, I'm going to take this corner out. It's supposed to be this. It's supposed to be this face. Okay, so I'm going to take this face, take that out, and then take that little triangle piece and do the sum of the forces to find out what are my total forces acting in the x prime direction. So there on the right you see the exploded view. The area of this bottom face, so if the area of the wedge we cut out is some delta A, some area that we, on that surface that we've cut out. That means this piece down here is delta A sine theta, because here's theta, and this area on this side is delta A cosine theta. That make sense? Okay. So now because we need to know the areas, if we in order to do some forces, we have to multiply the stresses times the areas. So you can see there on the diagram all the different forces we have. Right, we have a sigma x pulling on this side, sigma y pulling on this side, tau x, actually it should be tau yx pulling in this direction, tau xy pulling in that direction. Right, and then we have the stresses up there. So some of the forces. So some of the forces in the x prime direction. What are going to be the sum of the forces in the x prime direction? Look at a picture and tell me what the sum of the forces in the x prime direction are.
You're gonna
A leak, apparently. What are the sum of forces in the x prime direction? What's acting in the x prime direction?
There's normal stress. Acting in the x prime direction.
Right, so I have sigma prime, sigma sub x prime.
There's also shear stress. Acting.
Well, okay, but I'm summing the forces, not the stresses.
Right.
So I have to multiply that times delta A. Right, that's why it says sigma times delta A. Right, so that's acting in the x prime direction. What else is acting in the x prime direction? The sigma x have a component in the x prime direction.
Does sigma x have a component in the x direction, in the x prime direction?
Yeah. Oh, look at that. That's
Could that be sigma x
Delta A cos theta, right?
so the force that's acting on that left surface is sigma A, sigma x. Okay, so is it going to be plus or minus, first of all? Plus or minus?
Minus.
Minus, exactly in the negative direction. So minus sigma x times delta A cosine theta. That's the force. Is that acting entirely in the x prime direction?
What the cosine theta is.
What is x prime?
we multiply by cosine
And
theta?
so this piece here, right, that stress is sigma x. But the area on which that stress acts is delta A cosine theta. So the force is sigma x times delta A cosine theta. That is just that force. You see what I'm saying? This, wait a minute, oh, shoot, I can't put the meter stick. I don't know what happened to the meter stick.
Oh,
Field trip, go find.
class is over, you don't have the mirror stick.
I can't do that because,
There it is.
yeah.
I just wanted to tell us to wake up again. That was
All
awesome.
right.
How'd you notice?
So, this force is sigma x delta A cosine theta. It's stress times area, because delta A cosine theta is the area of that whole face. That's that force. Is 100% of that acting in the x prime direction? No, only a component of that is acting in the x prime direction. What is the component of that force acting in the x prime direction? How do I get the x prime component of that?
Just cosine theta again?
Times cosine theta again. Right, because this is my x prime direction. This is theta. So the component of sigma x delta A cosine theta acting in the x prime direction is sigma x delta A cosine theta cosine theta. Everybody see that? Yes?
Yeah.
Okay. What else do we have? What other forces do we have acting in the x prime direction?
And,
You can look at the picture over there.
yeah, the tau xi cosine theta.
Okay, so we have tau xy delta A cosine theta, that force
Times sin theta.
times the sine of theta. Is that positive or negative?
Negative.
Everybody see that? Okay, what else? Got two more forces acting on the, actually three more forces we haven't addressed. Is there a component of tau x prime y prime delta A that acts in the x prime direction? Yes or no?
Yes.
So there's this force here, hold on a second. This is the force. It's tau x prime y prime delta A. Is there a component of that force acting in the x prime direction?
No.
No, it's perpendicular, right? It's acting perpendicular to the face. So that one doesn't have an x prime component. What about the bottom two? Tau xy delta A sine of theta. Okay, what's its component in the x prime direction?
Times cosine theta.
Right. So I have tau xy delta A sine theta times cosine theta. Positive or negative?
Negative.
Negative.
It's not over.
And then the other one times, or times sin theta.
So then I have sigma y delta A sine theta
It's like sine over cosine.
times the sine of theta. Is that positive or negative?
Negative.
Negative.
Sine over sine. Sine squared.
You guys see that? Yeah?
Yeah.
So we got every force except for the shear stress on the x prime face contributes a force in the x prime direction. So if I solve that for sigma x prime, right, because that's what I'm trying to find, I'm trying to figure out what my new stress will be in this new configuration. I get sigma x, because I can divide through the delta a's, get rid of the delta a's, because we know that the sum of all those equals 0. So I end up with sigma x cosine squared theta plus sigma y sine squared theta plus tau xy times 2 sine theta cosine theta. Everybody see that? We got 2 tau xy sine theta cosine theta pieces we have the sine squared piece and the cosine squared piece. Okay? All right. Now we can use some trig substitutions. Sine squared plus cosine squared equals 1. And 2 sine theta cosine theta equals sine or cosine of 2 theta. I can't remember. Anyway, you remember the trig identity, that there's the double angle trig identity?
No, I mean, that's a,
I think it's cosine, and 2 sine theta cosine theta equals cosine 2 theta. So because if theta is 90 degrees, then it's 2 times, no, I can't read it. Cosine 2 theta over 2. Anyway, you do the substitution, and you end up with this. Sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times the cosine of 2 theta plus tau xy times the sine of 2 theta. Okay, so trust me, it gets better, but it looks ugly right now.
But how did you get the half?
So this is sigma x plus sigma y over 2 cosine squared theta plus sigma x minus sigma y over 2 times cosine squared theta. And this is, that's how you do it. You do sigma x plus sigma y and sigma x minus. You split this into the average and the deviation.
Can you just do sigma x plus, no?
No, you can't. In order to get rid of the sine squared plus cosine squared term, you have to split it into these two pieces.
Okay. And then why do you have the cosine 2 theta?
It's just the way that the math works out. Just, yeah, I was gonna say, I'm burning an awful lot of time just going through this in the first place.
Okay.
I'm afraid we're not gonna get to any practice problems. But anyway. So, sigma y prime, then, is essentially the same analysis, but now theta is 90 plus theta. So we added 90 degrees to all of our thetas, and we get sigma y prime equals sigma x plus sigma y divided by 2, plus sigma x minus sigma y divided by 2, cosine 2 theta, but now it's minus tau xy sine 2 theta. Okay, so the only difference there between those two is, oh yeah, this one's minus 2, sorry, is the sign of the terms. Plus terms become minus terms for y. And similarly, we can solve for tau x prime y prime. The strict shear stress on that face. And that's just going to equal minus sigma x minus sigma y over 2 sine 2 theta, excuse me, plus tau xy cosine 2 theta. Okay. So there's kind of a lot of ugliness in there. Doesn't necessarily seem neat and tidy, but that's about as simplified as it gets initially. Okay? So for any angle theta, I can calculate the new stress and strain. Well, the new stress, the new normal stress and shear stress, the new plane stress, using that theta and the original values. But usually the reason that we use this is because we want to find out what the maximum stress is
at a specific angle,
at a particular angle.
or the maximum stress over.
At what angle do you
Okay.
achieve the maximum stress, and what is that maximum stress? Right, because we're only concerning ourselves with, when is this thing going to break? When am I going to exceed the allowed stress? So if the allowed stress, for instance, is 120 megapascals, and I've got 100 megapascals here and 100 megapascals here, you'd be tempted to say, good, I didn't break the 120 megapascals. But in reality, if I have 100 here and 100 here, this is 100. I'm sorry. This is 100. This is 0. Right? right? Because 100 minus 100 divided by 2. Well, okay. Depends on what the theta is too. Let me back up. If it's 100 here and 100 here, you'd think you don't have it. You know, that you've not exceeded it. But what if I looked at 45 degrees? So if I have 100 here and 100 here, what's going to happen at 45 degrees? Or what's going to happen at minus 45 degrees? Or what's going to happen at 30 degrees? Is one of those perhaps going to exceed 120? Because somehow sigma x and sigma y might combine together to form something bigger. You see what I'm saying? So,
So,
go
sorry,
ahead.
do these equations work for just the outside ones, or would that also be like if you how we took the slice out of it? Would that work for the internal?
This
side?
works. This is for any point in a material.
Okay.
So you would do this at any point inside the structure. So what we did last time, we talked about combining stresses. We had sigma x, and we had what's the normal stress in the y direction, what's the normal stress in the z direction, all this different normal stresses and stuff on these beams, right? Well, if I have a normal stress in this direction and a normal stress in that direction, then I need to know what the total normal stress is on that little bit at some point in the material. I have to be able to do all 6 pieces of stress and add them all together appropriately. Okay, does that make sense? So at this point, we're just limiting ourselves to plane stress. So we're just looking at a 2-dimensional structure. But still, we need to know, in this 2-dimensional structure, what's the total stress? If I've got 100 here and 100 there, do I somewhere exceed the 120? In some orientation I might, right? You can imagine, if we both pull, if you pull that way 120, I pull this way 120, well, we end up with a net force that's greater than 120 in this direction. Right? Or, yeah, if you pull 100 here, if we pull 100 in each direction, then the total force is over 100. But the area on which that total force is acting may be more than the same area, so we've got to calculate it. So, we end up with these expressions. What we really care about is, what's the angle that's going to give us the biggest stress? Right? It's the maximum stress that we really care about. That's the point where it's going to yield. So how would we find the angle that's going to give us the maximum stress?
The derivative equals 0.
Right. We take the derivative with respect to the angle and set it equal to 0. You do that, and you find that the derivative of sigma x prime with respect to theta is minus sigma x minus sigma y over 2, because the first term has no derivative, the derivative first term is 0, times 2 sine of 2 theta plus tau xy times 2 cosine of 2 theta. Right, that's just the derivative of that first line there. Set that equal to 0, and we find that the tangent of theta p, which is the principal stress. P stands for principal. Tangent of theta p is equal to tau xy divided by sigma x minus sigma y over 2. So that angle, I'm sorry, tangent 2 theta p, I'll have to add 2. That angle, theta p, is the angle by which I must rotate this system in order so that I maximize or potentially minimize, right? I maximize or minimize these 2 values. Once I know that angle, I can take that angle and plug it back in up here to find out what those maximum and minimum values are. Tangent of 2 theta, tangent function is periodic on pi. Right? It's periodic with pi. So the tangent of 2 theta is periodic in values of theta p of pi over 2. So this gives 2 solutions. Theta p1 and theta p2. which are separated by pi over 2, or 90 degrees. One is the max and one is the min. So when I rotate it, theta p, one of these two will be a max. So let's say theta x prime is a max, then 90 degrees later, I'll have another point where the derivative is 0, and therefore theta y prime is a min, or vice versa. But the max and min values, the principal stresses, the maximum and minimum normal stresses, occur at theta x prime and theta y prime aligned along theta p's.
So-
Theta p's.
Okay, so you're saying once you do that math, you get this theta to rotate it, but is that then saying that you're still applying the original, like you said, that's.
So I'm applying 100 here and 120 there, whatever else, you know. I'm applying a stress here and a stress here.
Yeah.
As a result, within this material,
Mhm.
there's going to be a maximum stress in this direction.
But so it's not though if you actually rotate the physical thing, it's if you rotate your axis.
Right, you're just
Okay.
rotating your coordinates, because this is the physical thing that's experiencing these stresses. But that doesn't mean that these are the maximum stresses that occur in there. We have to find the maximum stress, because we gotta find out, is this thing gonna fail or not? So we have to then rotate this by theta p, and then we can find out what is that maximum and what are those maximum and minimum stresses, so we can know, are we safe or are we not safe?
But so our physical object doesn't.
Physical object doesn't move, our analysis moves,
Gotcha.
okay? Because if it yields in this direction, we don't care. We don't, yield is yield, whether it yields in this direction or that direction, it doesn't matter what direction it yields. The fact that it yields is problematic.
I'm
Okay.
just confused because of the squares.
Yeah, I understand. So this is just sort of how we're looking at it. The stress is applied, but we have to rotate it to a coordinate system that's convenient. Actually, if you look at these equations, they should look familiar to you. We've seen that same kind of format before. Anybody remember when that was? Parallel axis theorem. What, okay, well, yeah, you're in the right column. What do you use the parallel axis theorem on? What quantity?
Moments
Moments of inertia. Right, the moments of inertia. Remember when I talked about doing the same thing with the moments of inertia, rotating those to a different coordinate system? That's the same kinds of expressions, okay? It's all based on the same, it's driven by the same principles. Okay. So we have these three expressions, and we have this critical angle for maximum sigma p in each direction. Okay? I have something else? No, I don't. Okay. Shoot, I meant to put that other figure in there. Does anybody get your book?
Yeah.
Okay, so if you look on, here's the old books, I don't know if it's the same number, figure 9.8, or 9-8. In the current book, it's on page 449, in the current edition. Chapter 9, section 9.3, it's at the bottom of the page of section 9.3.
What page you say was?
It's, well, it doesn't matter, you go to 449 in mine. Go to section 9.3. All right, go back, there you go, right bottom of the left page, bottom of the right page there. What page is that, the right page?
445.
Okay, what figure number is that at the bottom?
98.
Okay, so it's still 9.8. So that figure 9.9-8, which I meant to include in here, kind of plots this out. Didn't put it in my notes because I was going to put it on the board, and then I didn't put it on the board. So this plots tau versus sigma. Okay, it's a plot of the tau versus sigma graph. And so essentially the sigma version here, the sigma axis, is sigma x minus sigma y divided by 2. The tau height is tau xy okay? And here is 2 theta p. The tangent of 2 theta p equals tau xy, the height, over sigma x minus sigma y divided by 2. Or, you could have another version of 2 theta p. This is 2 theta p 2, that's 2 theta p 1, and that's 2 theta p 2. Right, because 2 theta p 2 is 180 degrees from 2 theta p 1, because theta p 2 is 90 degrees from theta p 1. And here, we have exactly the same kind of configuration, except this is now minus tau xy, and this distance here, this coordinate here, is minus theta x minus theta y over 2. You see that? Okay. So that the length of this vector is the square root of theta x minus theta y over 2 squared plus tau xy squared. That's the length of that vector from the origin to that point.
Those values are 180 off, not 120.
Theta p is 90 off. 2 theta p is 180 off.
Oh, okay.
Okay. Okay. So, I know this looks a little obtuse to throw this graph up here. How are we doing? But it's actually going to make more sense when we come back to it later. Okay. I'm sensing that we're going to be pushing the next exam off by a day because I don't think we're going to get through this. Okay, but I think it's important that you understand where this comes from rather than just throwing a bunch of equations at you and say, here are the equations. Okay. So we have this funky radical dimension for the line out there, but there's something about this point out here that defines our system. Okay, we go up by tau xy, we go over by the half the difference between the x and the y. Okay, so we know what our input coordinates are. We go over that distance, we go up by tau xy, and that tells us how much we have to move it to get to this maximum normal stress. All right, notice all these values are the input values. Sigma x, sigma y, and tau xy. So we take our input values, kind of plug them into that graph, and it tells us how much we've got to rotate. Actually, it's 2 theta, but nonetheless, it tells us how much we've got to rotate in order to get to the point where we have maximum normal stress. Or how much we have to rotate, going the other direction, to get minimum normal stress. Does that make sense? Okay. We'll come back to that figure, so make sure you understand that you have that figure. Yes.
I didn't mean to cut you off.
I'm sorry.
The one direction always max, the other one min, or is it just kind of depending on the system?
It depends on the system. You'll see it more clearly next time. Okay. So now if I take this value of theta p and plug it back into these two expressions up here to solve for those maximum stresses, I get that the principal stresses, 1 and 2, corresponding to theta p1 and theta p2, are sigma x plus sigma y divided by 2 plus or minus the square root of sigma x minus sigma y divided by 2 squared plus tau xy squared. Because this stuff on the right-hand side here defines that line. Sigma x minus sigma y divided by 2 times the cosine of 2 theta, when theta equals theta p, plus tau xy times the sine of 2 theta times when theta equals theta p, defines this line. And so we're adding to it the square root of, did everybody see that?
So we don't actually need to truly know the angle to find the maximum. Because with that equation, we don't have theta p in there.
No, this, yeah, right, so we don't need to know what the angle is to find the maximum shear stress. But we need to know, but we don't know where that maximum shear stress occurs, or the maximum normal stress occurs,
It's
unless we
just
find the angle.
Yeah, but we can find the magnitude of it without,
Right, right.
okay.
You can find the magnitude using this, but then to find out where that magnitude occurs, you have to still solve for theta b.
Yeah.
Okay, but yes, the utility is we can get to the maximum value just by knowing what the originals are. We don't actually have to do the rotation to get there.
So first check just to see if you're so like if you are given those like the 100 here, 100 here, just to check to make sure you didn't go over the
Right.
maximum, you can just use that.
Right. And you notice, in the case of 100, 100, this term disappears. So it's the 100 plus 100 divided by 2, that's 100. So the shear stress determines
Okay.
whether you go up and down by the shear stress, by the amount of the shear stress. Again, this will all be a little bit clearer analytically. The analytical approach will be easier next time. Okay, we can do the same thing. Instead of taking the derivative of the normal stress with respect to theta, we can take the derivative of the shear stress with respect to theta to find the maximum and minimum shear stress. Right? So we do, well, I'll just write that over here. So we take d tau, d theta, set it equal to 0. That gives us that the tangent of theta s, where now theta s is the maximum shear stress, as opposed to the p, which is the principal stress, the normal stress. Tangent of 2 theta s again, sorry, equals minus sigma x minus sigma y divided by 2 over tau xy. Or, another way of writing it, that's equal to minus 1 over the tangent of 2 theta p. It is the multiplicative and additive inverse of the solution for the principal stress. Which means that theta s is equal to theta p plus or minus 45 degrees. So the angle at which we get the maximum shear stress is 45 degrees away from the angle at which we get the maximum principal stress. And the same is true of the minimums. So at that point then, tau max is equal to the square root of sigma x minus sigma y over 2 squared plus tau xy squared. We find the maximum shear stress, find out it's 45 degrees away from the maximum principal stress. You plug that same 45 degrees in here, and you end up finding out that this is the tau max is this extra term. Tau max is equal to that extra term. So in other words, the principal stresses are at some average. See, this is the average principal stress. So I can rewrite that as sigma average plus or minus that radical term. So that the principal stress is the average stress plus the maximum shear stress or minus the maximum shear stress. So the minimum is the average minus the maximum shear stress. The maximum is the average plus the maximum shear stress. And because it fails differently, the strength in shear is typically weaker than the normal strength, it still may fail here. So even though this is an appendage to that, right? So normally you look at it and say, well, this one's always going to be bigger than this. Potentially, it depends on what one of them could be compressive. If this one's always bigger than this, then what do I care about this? Well, the yield in shear is typically lower than the yield in tension. So it could still fail in shear and be good in tension.
I've got a question.
Yeah.
With our sigma x prime and sigma y prime, that equation, is sigma x plus sigma y over 2 plus sigma x, minus sigma y over 2? Are those supposed to be in parentheses, times cosine of 2 theta?
No.
No.
This one is by itself,
Okay,
because when we took the derivative, that one went away. Right, the first term went away because it's a constant.
right.
I was just
very
with it. Right.
It just seemed a little funky to me, especially.
So it's basically the average stress plus the average difference times cosine 2 theta plus the shear stress times cosine 2 theta. So the average difference is the difference between the two divided by 2. Because the half, if you're sigma x and sigma y here, then the average is here, and the difference is between like this. Okay, so it's a lot of stuff. We ended up with this expression, which is the one that you'll find in your book, I'm assuming, and now I have to check. Well, they have stress transformation, and then they have principal stresses, and the maximum in-plane shear stress. So they have all of that. They have the generic expression here, and maximum shear stress, both in on the equation sheet that you get to work with. Okay. But the important part of going through it in class is hopefully understand where that came from. Okay. Because in life you need to figure stuff out, not just know stuff. Okay. So we didn't get to any problems. Actually, maybe I don't know if we'll do the problems next time or not. I'll have to figure out. I'll have to look at the schedule and see. Because I'm going to teach, we can do the problems, but then I'm going to teach you another way of doing the same analysis, another way of thinking about the same analysis, that may actually make the problems easier to do.
So, when's the next homework day, is that
Monday.
Monday?
Yeah, because this is all new. This is chapter 9. We're up to, right, this is chapter 9. So we finished chapter 8 on Wednesday, so chapter 8 homework's due on Monday.
When's the test? Do you know, off the top of your head?
That's what I need to figure out in the context of whether I'm going to try to do some example problems here or move on. Again, like I said, the technique that I'm going to show you next, called Moore circles, is actually, to me anyway, a mechanically easier tool to use to solve these problems. It's actually mathematically no different than what we've got right here. It's just another way of looking at these expressions. Okay. We got.
Did we do more circles before?
Did we do more?
You mentioned it before?
In here?
Just in general.
I have mentioned more circles in material science.
Yes,
But I
never
did
So
not-
it's
we did not do
really
them.
familiar to us.
Okay. We didn't, I don't think we ever did any more circles analysis.
I don't think so, but I think you had mentioned it in class.
Okay.
Because it sounded really familiar to them.
Yeah.
Yeah, I'm gonna try to work on possibly more tonight.
Because we don't really talk about stress distribution and static. Just talk about forces.
You going on studio?
Yeah.
I'm sorry.
Okay.
Well, I'm not going home.
Yeah.
I'm trying to go to soccer games.
I'm gonna be around, so I think I'm gonna try tonight. I'm gonna be working stuff.
Yeah, I gotta take it tomorrow, so I'm not going.
Yeah, we're